Okay, so this is video number 2 in equilibrium. So today we're going to get into the theory piece. So we're going to be talking about Le Chatelier's principle. So Le Chatelier's principle basically tells us that anytime a system is at equilibrium, we can disturb that system and cause it to reestablish equilibrium. So you're going to find in this video, we're going to talk about 6 different stressors and what impact they have on that equilibrium position. And we're always going to be using Le Chatelier's principle to help us determine what direction the shift is going to be. So you're going to find that we kind of tend to talk about 3 general shifts. So sometimes we're going to say that the system shifts to the right, which means we are going to be turning more reactants into products to be able to reestablish that equilibrium. In other cases, we are going to say that the system shifts to the left, which means that we are going to be taking products and turning them back into reactants to reestablish that equilibrium. Okay, there are some other terms we use too. Sometimes we say shifts to the right, but sometimes we also say, let me just change the color here, that it is going to favor, well, that's not writing where I wanted to, favors products. And that's because in shifting to the right, we're going to create more products, therefore we favor products. If we are saying that it's shifting to the left, we will sometimes say that it favors reactants. Again, because it's going to be creating more of those reactants. Okay, the third possible option is going to be for no shift to happen. Okay, so how you're going to be able to predict whether it's going to shift right, shift left, or not shift is going to be by applying Le Chatelier's principle. So what this principle basically tells us is that whatever we do to the system, it's going to try to counteract that. So if we were to increase something, it wants to decrease it because it wants to do the opposite. So when you do Le Chatelier questions, you want to approach it in a very logical manner because that's usually going to be your best way of doing it. So I generally tell you guys that there are 3 thought processes you want to go through. So the first thing you always want to think about is, what did we do? So what did we do to the system? What did we change? How did we change it? Did we increase it? Did we decrease it? What did we do? The second thing we want to think about is, what is the system going to do? And it's going to do whatever the opposite is of what we did. So let's say we increase the concentration of chlorine gas. The system is going to want to do the opposite. So it's going to want to decrease the concentration of the chlorine gas. Once we decide what the system is going to do, then that final step is going to be to show the direction of shift. So how you're going to do this is based off of what the system is attempting to do. If it's trying to make more of something, it has to shift towards that something so that it creates more of it, right? If you think about how we generally write our arrows, right, that means the reactants are turning into products. So we would be increasing the amount of products, but we would also be decreasing the amount of reactants. Whereas if we were shifting in this direction, we would actually be decreasing the amount of products and increasing the amount of reactants. So that's how we're going to decide what the direction of shift is. We're going to figure out, what is the system trying to do? Is it trying to increase or decrease it? And then we're going to decide the appropriate direction of shift. So the different factors we're going to look at concentration, pressure, volume, temperature, catalyst, and addition of an inert gas. So some of these are definitely easier than others, and some of them are definitely more complicated than others. Most important piece, practice. Okay, you're going to find whether you're in class learning this lesson or you're at home learning this lesson, usually it seems really easy during the lesson, but then when you try it on your own, sometimes then you realize that you don't quite have the thought process down right. So really important to make sure that you are practicing it. Okay, so first one we're going to look at, we are going to look at concentration. So really important to recognize that when we are talking about concentration, this only applies to some states. This only applies to aqueous and gas. Okay, and the reason for that is a solid and a liquid, concentration is dependent on density, and we're not changing its density. So why I say to make sure that you notice this is if it tells you that it increases the amount of a solid or a liquid, that actually has no impact on the equilibrium position, okay? It's only going to matter if it's aqueous or gas. So really important to make sure that you are looking at your state so that you say the right shift. Because I promise you, there are questions on the diploma where they throw a solid in there just to see if you know that a solid shouldn't shift, okay? So what happens with the change in concentration? So it's going to shift the equilibrium position. So generally these questions will tell you that they add or remove something. So if we add something, that means we increase the concentration of whichever chemical. So the system is going to want to decrease the concentration of that same chemical. The only way to do that is to shift away from whichever side has that chemical. Okay, the opposite, if we increased a concentration, oh wait, I already did increase. If we decrease the concentration of something, the system would want to increase it, and it would shift towards that particular chemical. So we have an example here. So we have an iron 3 ion, we have thiocyanate ion, and then we have an iron thiocyanate complex ion. So the change is to add SCN minus. So if we add SCN minus, that means that we just, of course I can't do an arrow on here, we just increased the concentration of that SCN. So if that's what we did, we increased the SCN. The system wants to do the opposite. So the system wants to decrease the concentration of the SCN. Okay, so the question told us what the change was. We wrote that down, that we figured out what is the opposite, right? Increasing and decreasing, those are opposite to each other. So to be able to decrease the amount of SCN minus, our system has to shift away from it. That means it's going, that's a horrible arrow. Well, let's pretend it's a nice straight arrow. It is going to shift to the right. So what that means is my system has counteracted the change, which we did, increasing the SCN by decreasing the SCN. So if we look individually at each one of these chemicals, right, we're going to find initially we increased this. But now the system just decreased it by shifting away from it. So that means we also changed the concentration of iron 3, and we also changed the concentration of FeSCN2+. So although we didn't do that initially, by the system shifting, it will impact that as well. So again, my arrow is going to the right. It's going away from the iron 3. So that means this concentration is going to decrease. It's going towards the FeSCN2+, so this one is going to increase, okay? So that's how concentration changes work. Make sure the state is aqueous, which in this case everything was aqueous, so we knew it could shift. We increase the SCN. System wants to decrease it because that's the opposite. The only way to decrease it is to shift away from it. So next factor to look at is temperature. So just like concentration is going to impact my equilibrium position, so is temperature. So temperature tends to be, I'd say, probably the most complicated one because you have to look at a couple of other variables to help you decide this. So anytime a question starts talking about temperature, you need to determine which direction is endothermic and which direction is exothermic. That's the only way you're going to be able to decide which way it's going to shift. If you don't have that information, it's next to impossible to decide which way it is going to shift, okay? So, question is going to show you in one of two ways that something is endothermic or exothermic. So one way it's going to show you is kind of like this question here, where you'll see that this number is included on either the reactant side or the product side. Okay, the other way that you will sometimes see it is you'll see kind of tabbed off on the side, it's going to say delta H equals. And then either it's going to be a positive or it's going to be a negative number. Okay, for now, we only care about is delta H positive or negative, or is the heat term written on the reactant or the product side? That's really all we care about. That's how we're currently going to decide endothermic or exothermic, okay? So once you decide whether the reaction is endothermic or exothermic in the forward direction, you automatically know what it's going to be in the reverse direction because it's going to be the opposite, okay? So if it is written on the reactant side, right? So here it's written on the reactant side, or if it's tabbed off to the side and it is a positive, okay, that is going to mean that it is endothermic in the forward direction. If you find that that's not the case, though, and it is either negative or it's over on the product side, then that means it's exothermic in the forward direction. Okay, so where it's written or what the sign is going to tell you what it is. So once I know whether it's exothermic or endothermic in the forward direction, then I can start making decisions as to which way it is going to shift. So if we look at this example here, we have the N2O4 plus 58 kilojoules to give us 2 NO2. So because it is written on the reactant side, that is telling us that the forward direction is going to be endo, which by default means the reverse is going to be exo. So I usually like to write over my arrows. Of course, now I'm getting really scrunched up in here. That because the forward arrow is there, I like to write endo over it. And then because my reverse arrow is on the bottom, I like to write exo with that. Then that helps me to recognize which direction is what. So step one, before you even really get to the question, is I need to decide which direction is endothermic and which direction is exothermic. So you think about it, exothermic reaction, right? Those are the ones where you touch the outside of the beaker and it feels nice and hot. Okay, an endothermic reaction, you touch the outside of the beaker and it feels cold. So those are important things to think about because when we think about temperature changes, that's what we need to do when we're thinking about what's the opposite, right? So our two options for temperature change are to increase the temperature or to decrease the temperature. So if we were to increase the temperature, the system wants to decrease the temperature. The way to decrease the temperature is to go in the endothermic direction because then it's going to feel colder and that's going to bring that temperature back down. Right? Whereas if we made it colder, it wants to make it hotter, so it's going to go in the exothermic direction. So that's why you have to be able to decide which way is endo and which way is exo before you really start to answer the question, okay? So again, going back to our example, we've already decided that the forward is endo and the reverse is exo because we had the heat term on the reactant side. So the change is to add heat energy. So that means we just increased the temperature, right? That's what we did by adding heat. We made it hotter. So the system wants to do the opposite. So the system is going to want to decrease the temperature. So if it wants to decrease the temperature, the way to decrease it and make it cold is going to be to go in the endothermic direction. So now we know what the system wants to do. We know the system wants to go in the endothermic direction. Well, we've already decided that the endothermic direction was the forward direction. So we know that in this particular case, this reaction is going to shift to the right as a response to us having increased the temperature. Okay, so you'll notice over here there are some images. This is basically our N2O4 equilibrium tubes. So you'll notice in this first picture we have just N2O4. It's colorless. If you notice, as we go this way, it gets darker and darker. So that brown color, if we only have two chemicals in here, has to be due to the NO2. So what we're seeing happening when we look at these temperatures is the warmer we make it, the more brown that tube becomes. And that's because we are creating more and more NO2. So this is how you can help use colors to see what it's shifted to. So we're often going to use a control, right? And so a control means we know exactly what's in it, and we can see what color it is. And then we can compare really easily to say, oh, look, this got darker, and oh, this got darker as well, okay? So that's how temperature works. Start by figuring out which direction is endothermic and which direction is exothermic. Then think about what did we do to the temperature? What is the system going to do? And then does that equate to an endothermic or exothermic reaction based on whether it's getting colder or getting hotter? Okay, so next one is pressure. So when we are talking about pressure, pressure only matters for gas molecules. And the reason it only matters for gas molecules is they are the only molecules that are actually going to create pressure on the walls of a container. Right? If you think back to when we did the gases unit last year, we talked about how pressure had to do with how many molecules and how hard they were hitting, right? And we said the more molecules and the more force with which they hit, the more pressure would be associated with that. Whereas the less molecules or the less force with which they hit, there would be less pressure. So when it comes to pressure questions, I only care about gas molecules. I don't care if I have a solid, I have a liquid, I have an aqueous. I'm basically going to ignore them within my chemical equation. So what we are going to find in all of these questions, we always have to be relating it back to how many gas molecules do I have, right? More molecules is going to equal more pressure, and less molecules is going to equal less pressure. So what we're going to find is in some of these cases, we may find there is no shift even if I do change the pressure. So if this was balanced with a 2 and this was balanced with a 2, there's equal pressure on both sides. So creating more products doesn't increase or decrease the pressure. Just like increasing the reactants or decreasing it also doesn't impact the pressure. But in this case, when I look at this particular question, I have 1 gas molecule for the reactants, and I have 2 gas molecules for the products, right? And that's just coming from these coefficients. And if I had multiple products and they were both gases, then I would just add up and get the sum of those coefficients. So what this means is for every 1 N2O4, if that decomposes, it's going to create 2 NO2s. Whereas if it goes in the opposite direction, 2 NO2s can combine together to make 1 N2O4. So this is going to be able to shift if I have changes in pressure. So when we are talking about pressure changes, you want to think, what did we do? Did we increase or decrease the pressure? What does the system want to do? Again, it's going to be the opposite. So if we decide that the system is trying to decrease the pressure, it's going to shift in the direction of the side that has less gas molecules, because less molecules means less pressure. If my system is trying to increase the pressure, it is going to shift to the side with more molecules, because more molecules equals more pressure. So generally, pressure tends to be pretty straightforward. Count your gas molecules on both sides. If they're the same, there will be no shift. If they're different, we need to decide, is the system trying to increase or decrease it, and then we can go from there. So looking at this example, the change is a decrease in pressure. So that means we just decreased the pressure. So the system wants to do the opposite. So the opposite of a decrease is going to be to increase. So the system is going to want to increase the pressure. The way to increase the pressure is to shift to the side with more molecules. So this side has 1, this side has 2. It is going to shift to the right. And if you think about it, this is the same one that we just talked about in the last case, right? The exact same equation. See, N2O4 and NO2. Remember we talked about color? We said the N2O4 was colorless and the NO2 was brown. So in changing the pressure, we are also going to see a color change happen. We are going to see that it's going to become more brown over time because we have increased the concentration of NO2 by shifting over to the right. Okay, the next change is a change in volume. So volume changes are basically how we create pressure changes. And that's because if you remember, again, back to last year in gases, we talked about how volume and pressure were related, right? We said that they were inversely related. We often talked about examples of syringes, right? Because a syringe, you can compress it. By compressing it, you've changed the volume and made it smaller. But by doing that, you have increased the pressure. So if you can do a pressure change question, you can do a volume change question. So the only additional step required in this one is to figure out at the beginning, if we did this, the volume, what does that mean we did to the pressure? And then it turns entirely into a pressure-based question, okay? So they're inversely related. So that's important to know as you determine this. So in this case, the change is a decrease in volume. So that means we just decrease the volume. But we don't want to deal with volume, we want to deal with pressure. So a decrease in volume means an increase in pressure, right? Because they are inversely proportional. So this is all what we did. So now we need to think about what is our system going to do, right? And the system is going to respond to that pressure change. So if the pressure change by us was to increase the pressure, the system wants to decrease the pressure. So to decrease the pressure, it would shift to the side with less molecules. When we look at this, gas and gas, so 1 plus 1, we have 2 gas molecules on this side. On this side over here, it's a gas, we also have 2 gas molecules. So in this case, there would be no shift. Maybe I'll type that instead of trying to write it. No shift. Okay, and there's no shift because it can't counteract the change. The whole point of Le Chatelier's is to counteract what we have done. It can't counteract. Shifting towards products doesn't change anything. Shifting towards reactants doesn't change anything. So there will be no shift. However, that doesn't mean our concentrations won't change. It's just they're all going to change in the same way. And the reason they're going to change is if you think about the units of concentration, they are moles per liter. By changing the volume of the container, we have just changed how many liters we have. So in this case, even though there is no shift, we're going to find that all of these concentrations are going to change, right? So go back to what we did. We decreased the volume. So we just made this number smaller, that's down here. By making the number on the bottom smaller, we overall have increased the concentration of everything. So although there's no shift, individually, every single concentration went up because we changed the size of the container. So really important to make sure you read questions to see, is it asking for a shift or is it asking for a change in concentration? Because sometimes there will be questions where there is no shift, but we didn't ask you about a shift. We asked you about a change in concentration. And then you guys get them wrong because you're like, there's no shift, so there's no change. But then the question wasn't asking you about a shift, it was asking you about a concentration change. So recognize that changing the volume, even if there is no shift, will lead to a concentration change. If there was a shift, that would also lead to a concentration change. Okay, so that's volume. We're going to relate it back to pressure. We're going to basically treat it as a pressure change question. So the last 2 changes are nice and easy ones. Catalyst. You know, a catalyst makes something happen faster. So when we talked about equilibrium in the last video, we talked about how it means equal rates. So a catalyst works by increasing the rate of a reaction, but what we find is that it increases both the rate of the forward and the rate of the reverse by the same amount, which means it doesn't actually impact your equilibrium position. All it's going to do is let you reach equilibrium faster. So if ever a question talks about the addition of a catalyst, it has no impact on your actual equilibrium position, and no impact on your equilibrium concentrations. It just lets you get there faster. Okay, the last one is the addition of an inert gas. Okay, generally when we're talking inert gas, we're talking about one of the halogens, so like helium, neon, that type of thing. Sometimes it will say inert gas, and sometimes it will give you one of those. You guys tend to overthink this one significantly. this is no change. Okay, there's usually some of you that are like, go all crazy and get into pressure change because you're like, oh, but there's more molecules. Don't go there. Just know inert gas, no change, because it's simply occupying empty space. Therefore, there is no change. So the four you really have to concern yourself with are concentration, temperature, pressure, and volume. The catalyst and the inert gas, all you literally need to know is that they don't change anything. Okay, so not only do you have to be able to figure out how a reaction is going to shift, you also have to be able to graph and interpret that graph and figure out what it's going to mean. Okay, so when we are graphing equilibrium, these tend to be more, I would say, a qualitative graph as compared to a quantitative graph. And that's because when we shift something, we don't know how it's going to shift, right? Not how it's going to shift. We know how it's going to shift, but we don't know the quantity by which it is going to shift, which is why I say they become qualitative. They might be quantitative at the beginning because it might give you some initial concentrations, but once you start getting into all the shifts, they become entirely qualitative, and we're really just looking for the correct directions of shift. Okay, so here's the example we are going to work with. So we're going to work with nitrogen plus 3 hydrogens to give us 2 ammonias. Formatting went kind of wonky on this, and I really don't know why. So over here, this is our delta H, okay? So we're looking at the fact that it is negative, right? Remember, a negative delta H tells us that the forward reaction is going to be exothermic, okay? So we are given some initial concentrations. We are told that after 5 seconds, equilibrium is reached, and we're given those concentrations. And then we get into all the qualitative stuff. So A and B will be quantitative because it did give us some actual numbers to work with. But once we get to C and D and E, these become entirely qualitative because we don't know by how much it's going to shift. So really what we're looking for is, did you draw it shifting in the correct direction, okay? So looking at this graphing equilibrium example, switched over to the whiteboard because I don't think I have the skills to draw this on the little tiny screen. So what you can see is we have nitrogen plus 3 hydrogen to give us 2 ammonias. We were told that delta H is negative 92 kilojoules. So it starts out quantitative, and that it did give us some data, right? So it told us that the initial concentration of nitrogen was 1.5. So I started by putting a dot for nitrogen at 1.5. Okay, you'll notice I use different colors, and I do that because then it's easy to distinguish the lines. Otherwise, when they all start crossing, we sometimes get confused. Okay, then hydrogen, it said it started at 2.5, so I put a dot up here. And then ammonia, it said it started at 0.5, so I put a dot down here. Okay, B tells us that after 5 seconds, equilibrium is established, and it gave us some new concentrations. So it told us that the nitrogen at 5 seconds was going to be 1, and then that both the hydrogen and the ammonia were going to be coming in at 1.5. So we need to connect these dots. We are going to connect them using smooth curves. Okay, so it's not a straight line. I'm not taking a ruler and drawing it. I am going to curve it. And I'm going to do the same for all of these. We're going to draw curved lines. Okay, so then, once we have those curved lines, right, and this should look like what you guys drew in your graphs for your Cheerio exchange. So we have those nice curved lines. We are now at equilibrium. Because we are at equilibrium, that means our concentration shouldn't change. So we're then going to draw straight lines going across. I'm only going to draw them to 10 seconds, and that's because I can see by looking at C that it tells me that at 10 seconds I did something. So straight line, or as best of a straight line as you can, over to 10 seconds. I know these two lines are together, but just kind of put one on top of the other. Okay, so once we have that, that ends our quantitative stuff. Now we get into qualitative and having to apply Le Chatelier's. So when we look at this, C told us that at 10 seconds, the temperature was increased. So we want to think about what does that mean. So we just increased the temperature. The system wants to do the opposite, which is to decrease the temperature. So it wants to make it colder. The way to make it colder is going to be to go in the endothermic direction. So we need to go back to our equation. We need to look at what that delta H is and use that to help us decide. So when we look at it, delta H is a negative number. The fact that it is negative tells me that the forward is going to be exothermic, which means the reverse is going to be the opposite, and it's going to be endothermic. So we've just decided that our system needs to shift in the endothermic direction, which means it's going to go that way, okay? And going towards the reactants is going to increase my nitrogen, it's going to increase my hydrogen, but the ammonia is going to go down. So we look at our nitrogen, I have that in green. So we are going to slowly curve it up and then make it straight until 20 seconds. Again, because I know 20 seconds is the next time that I change something. We're going to do the same for hydrogen. I'm going to go to it. We're going to slowly curve it up and extend it over to that 20-second mark. The ammonia, though, we're going to do the opposite. Because we shifted away from it, we know its concentration needs to go down. So again, a smooth curve going down. Okay, by how much you go up or go down, we're not looking at that. We're really just looking for, did it go in the right direction? Did it go up when it should have gone up? Did it go down when it should have gone down? So you will notice that always for temperature change, just a nice smooth curve right away, okay? So our next change, or D, says that at 20 seconds, we decrease the volume. So we decrease the volume. When it comes to volume changes, we need to convert them to pressure changes. So a decrease in volume means an increase in pressure. Our system wants to do the opposite. So if we increase the pressure, it wants to decrease the pressure. It's going to decrease the pressure by favoring the side that has less molecules. So we're going to look at it. Everything is a gas, right? That's the first thing I want to do, make sure everything is a gas so I'm counting the right things. So I have 1 and 3. So I have 4 gas molecules on the reactant side. I look at the product side, I only have 2 because the ammonia is balanced with the 2. So if my system is trying to decrease the pressure, it's going to shift to the side with less molecules. So it is going to go ahead and shift towards the products. What you're going to find those with volume changes, these don't have smooth curves. Well, they do, but not initially. First thing we need to do is we need to show the impact of the volume change. So you're going to find that every time you are graphing, if you see that all the lines immediately all go up or all go down, that's basically telling you immediately that there was a volume change. So in this case, we decrease the volume. So if we think about concentration, right, and the fact that concentration is measured in terms of moles per liter. By decreasing the volume, we just made the number on the bottom smaller, which means that all of our concentrations, when we did that volume change, will all have increased. So we're going to draw a vertical line going up because they've all increased for every single one of these. Okay, so that vertical line going up is the impact of the volume change on my system at equilibrium. Now we actually have to show how the system is responding using Le Chatelier's, which is going to be that shifting part. And so this is where we're going to go into our smooth curve to show the direction. So because it is shifting over towards the products, the one that is going up is going to be the ammonia. So the ammonia is going to curve up and then become a flat line. The nitrogen and the hydrogen are going to do the opposite. They're going to curve down and become a flat line. Okay, this is why having multiple colors, okay, the different colors make it kind of easy to see, especially when all our lines start to crisscross. So the last change is that 30-second a catalyst is added. We talked about a catalyst, we said it does nothing. So all we're gonna do is just extend our line past the 30 seconds. We don't have to draw any shifting. I'll erase that little curve down to my line. But that is what okay, so that was graphing it, but you do also have to be able to interpret the graphs. So here's a graph provided to you. You need to be able to look at it and basically decide what happened where, right? So this particular system we're told is 2NO2 giving us N2O4 plus heat. So there are some things that I can look for when I am going in this direction, right? Knowing whether I should have spikes or smooth curves is really going to help me eliminate some options. So if you think back to the example we just did, temperature change is the only change where everything is going to go immediately into a smooth curve. So if I see no spikes, I know it had to be temperature. I'll still have to decide whether it was increase or a decrease in temperature, but I know it's temperature. If I see that all my lines spike up or spike down, and all of them, I know it had to be a volume change resulting in a pressure change. If I see that only one line spikes, we didn't graph that in the last example, but if only one spikes, that's a concentration change. Where if it went up, that means we increase that thing. If the spike went down, that means we decrease it. So some things are actually pretty easy to spot, and some are a little bit harder to spot. So in this particular example, you can see here we started with 2 moles per liter and 5 moles per liter. Right here, at about 4 seconds, based off the fact that 5 is here, we reached equilibrium. We know we reached equilibrium because our lines become flat. And that's what's defined as equilibrium, right? Things are going to stop changing. Once we reach here, though, something happened. And I know something happened because it didn't stay flat anymore, right? We disturbed equilibrium. So I want to look. Okay, I see this line spiked up. I also see this line spiked up. So both lines spiked. From that, I know this has to be a volume change because only volume change leads to all my lines spiking. The question just becomes, is it an increase or a decrease? So I can go through all of Le Chatelier's, but I really don't have to, right? If we think again about the fact that concentration, hey Jana. Okay, so because this is moles per liter, we can look at what happened to the concentration. We see that overall it went up. The only way for it to have gone up, because we're not changing the number of moles, is for the liters to have gone down. So from that, I know that the change must have been a decrease in volume. And I don't even have to go to Le Chatelier's. Some I will, but some I won't, okay? So next change, right, here we go. We reestablish equilibrium because it gets flat and it gets flat. But then right here, we do something else. And we know we do something because the line stops being flat. So when I look at it, we have a smooth curve and a smooth curve. That's telling me this has to be a temperature change because that's the only one that's smooth and smooth. So for this one, I do actually have to use Le Chatelier's to try to figure out the direction, not the direction of shift. I can figure out the direction of shift from what my curve did, but I need to figure out increase or decrease in temperature. So pick one of the two lines. It doesn't really matter which one. Let's look at NO2, which is the blue one here. We can see that it went up. So we know from our graph that the NO2 went up. We also know from our graph that the N2O4 went down. So for the N2O4 to have gone down and this to have gone up, we must have shifted that way, right? That's the only way the shift makes sense. So looking at this, we now have to figure out if the system went in the endothermic or exothermic direction. So because heat is over here on the product side, we know that the forward was exo. So from this, we know that this system just went in the endothermic direction. So if it went in the endothermic direction, the system just got colder. So it decreased the temperature, which means we did the opposite and we increased the temperature. Okay, so those are the ones that require quite a bit of work as the temperature changes. Volume change is pretty straightforward, and so is concentration change. So we've decided what happened there. So we disturbed it, it reestablished equilibrium, and then right here we disturbed it again. So if I look at the lines, This is a smooth curve. This one spikes down. So because only one spikes, I know this has to be a concentration change. I know immediately which one it is. It's the NO2 because that's the line that went straight down. And this immediate response is always going to be what we did. So I know just from looking at this graph, the change was to decrease the concentration of the NO2, right? And then if you look at how that line curves, you can see that the system brought it back up, which was the system reestablishing equilibrium by increasing the concentration of NO2. So these ones tend to be a little bit easier to interpret because you only have so many options, whereas drawing them definitely requires more work. Okay, so that is Le Chatelier's. Tomorrow we are going to be doing a lab on Le Chatelier's to really be able to see if you understand how to apply it.